Section. Introduction. Generative models have truly transformed the field of artificial intelligence, opening up a wide range of applications. These models have shown an impressive ability to work with different types of data, but it's in the realm of text where we've seen the most dramatic advancements. In just a few years, large language models, LLMs, have evolved from creating simple sentences to generating complex stories, code, and tackling many new tasks. This progress is marked by significant developments like the Transformer architecture, BERT, and the GPT series. At the core of these advancements are probabilistic models that are trained on huge datasets without specific guidance, aiming to predict or fill in missing parts of the data. This training approach helps estimate the underlying probability of the data, and as these models grow in size, they start to exhibit remarkable capabilities, such as reasoning. In our study, we're exploring how the probabilistic nature of autoregressive LLMs interacts with the data they're trained on. Specifically, we're interested in how the direction of time affects their ability to model both natural and synthetic languages. Autoregressive LLMs, like the GPT series, are trained to predict the next piece of information, token, based on the previous ones in a sequence. This process uses the natural order of time in the data. The model works by reading a sequence of tokens and then predicting the next token by estimating the probability distribution over all possible tokens. Essentially, for a sequence of tokens, the model calculates the likelihood of this sequence by multiplying the estimated probabilities of each token given the previous ones. This method allows the model to break down the prediction process into smaller, manageable steps, which has several benefits. For example, it enables efficient training and data compression, and it allows for generating new sequences token by token. Such models have significantly scaled up in terms of the number of parameters and the size of the datasets they're trained on. This scaling has led to fascinating outcomes, including the discovery of scaling laws and the emergence of complex behaviors like performing arithmetic operations, computing tasks, and achieving high-level language proficiency. However, it's not immediately clear why using the natural direction of time is the best approach for predicting token probabilities. To investigate this, we consider reversing the direction of time, essentially training models on data sequences presented in reverse order. By doing this, we aim to compare the performance of models trained in the forward, natural time direction, and backward, reverse time direction, manners on the same tasks. This leads us to our main question. How do the forward and backward probability estimates differ for a given dataset? We hypothesize that there might be significant differences in how these models approximate the underlying probability of the data, depending on the direction of time used during training. Section summary. Generative models, particularly large language models, LLMs, like GPTs, have made significant progress in generating coherent text and performing various tasks by training on vast amounts of data using probabilistic models. Autoregressive LLMs, such as GPTs, factorize joint probabilities into conditional probabilities for each token, allowing for parallelization of training and natural sampling from the probability distribution. Investigating the influence of time directionality on the ability of LLMs to model languages, the study explores training models on time-flipped datasets to estimate probabilities backward, revealing substantial differences between forward and backward measures for certain architectures and hyperparameters. Section. We train large language models, LLMs, by following these steps. We first pick sequences of n consecutive words or tokens from our dataset. Then, for each token in the sequence, we predict its probability based on the tokens that come before it in a forward, FW, model, or the tokens that come after it in a backward, BW, model. We calculate a loss, which is a measure of how far off our predictions are, for each token in the sequence. This loss is summed up across all tokens, and we use this sum to make adjustments to our model to improve its predictions. We repeat this process to continually refine our model's accuracy. In most cases, the loss we focus on is called the cross-entropy loss. This is calculated by taking the negative logarithm of the predicted probability of the actual token that appears in the sequence. The cross-entropy loss is special because it has certain properties that make it uniquely suitable for this task. Essentially, it tells us how many bits of information are needed to encode the sequence based on the model's predictions. The fewer bits needed, the better the model's predictions are. For both the forward and backward models, we calculate the cross-entropy loss for each token. If we sum up these losses across all tokens, it's equivalent to taking the negative logarithm of the probability of the entire sequence according to the model. If the forward and backward models are equally good, their cross-entropy losses will be the same. When we look at the average of these summed losses over many sequences, it breaks down into two parts. One part measures how different the model's predictions are from the actual distribution of sequences, using something called Kullback-Leibler divergence, and the other part is the inherent unpredictability of the sequence itself, measured by entropy. Interestingly, even if a forward and a backward model learn the sequence distribution equally well, the loss for each token might not be the same between the two models, though their total losses across all tokens will match. This can lead to different insights into how the model understands the sequence. For example, in a simple dataset where we multiply two numbers to get a product, the forward model might focus more on the numbers being multiplied, while the backward model might spread its attention more evenly across all parts of the equation. This observation suggests that if both models learn the sequence distribution equally well, their average losses should be similar. However, if there's a significant difference in their losses, it indicates that the sequence distribution might be easier to learn in one direction than the other. This difference in learnability can become apparent across various types of data and model configurations, showing a consistent pattern of difference in the losses of forward and backward models. Section summary. The training of language models involves sampling sequences of consecutive tokens from the dataset, making predictions for each token, computing the cross-entropy loss based on the predicted probabilities, and optimizing the loss through gradient steps. The cross-entropy loss measures the number of nats, lane, 2, times the number of bits, needed to compress the sequence using the model's estimated probabilities. Additionally, the difference between forward and backward log perplexities can reflect an asymmetry in the learnability of the true measure by the models, leading to consistent differences across various types of data and model configurations. Section: Setup and Plan. In this section, we discuss our setup and plan for exploring a phenomenon we call the arrow of time, AOT, in language models. We've noticed that when comparing forward, FW, and backward, BW, language models, meaning models that predict the next word in a sentence versus those that predict the previous word, there's a difference in their performance. This difference isn't due to the dataset, the structure of the models, or the settings we use. It's all about whether the model predicts words forward or backward. When a dataset shows this kind of difference, we say it has an AOT with respect to the model and the length of the text snippet, or context, we're looking at. We're curious about several things. Does this AOT exist in large collections of natural language data? Does it change based on the language of the text? Does the length of the text snippet we're looking at matter? Can we come up with a theory to explain why this AOT exists? Is it possible to create simple, artificial datasets that also show this AOT? Can we explain the existence of an AOT using basic mathematical principles? What happens as we make our models larger and larger? We've organized our paper to tackle these questions step by step. We start by looking for the AOT in different settings, different languages, model designs, settings, and text snippet lengths. Then, we try to understand the theoretical reasons behind the AOT, starting with a simple artificial dataset and moving to more complex ones. Finally, we wrap up with a summary of our findings and suggest directions for future research. Our discussion on related work shows that the idea of training language models on reverse text isn't new and has been used in various contexts, like machine translation and improving language model performance. However, our focus is different. We're specifically interested in comparing the learning outcomes of FW and BW models to understand the AOT phenomenon better. In our experiments with natural language, we first confirm the presence of an AOT using GPT-2 models on English and French texts. We then expand our investigation to include over 50 different setups, covering various model architectures, model sizes, text snippet lengths, and languages. Throughout, we ensure that any differences in model performance are solely due to the order in which words are predicted, not any other factors. For these experiments, we use the CC100 dataset, which offers a large and diverse collection of texts in various languages. We train a tokenizer from scratch for each language, ensuring it matches the specifications of the GPT-2 model, including the vocabulary size and the inclusion of a special token to indicate the beginning of a sentence. We carefully prepare our data to ensure each word is presented with sufficient context, adjusting the sequence length and the way we split the dataset accordingly. We reserve a portion of the data for validation to ensure our findings are robust. Section Summary. The section, Setup and Plan, discusses the investigation of an arrow of time, AOT, in large natural language datasets, considering factors such as language, context length, and theoretical framework. The paper aims to explore the presence of an AOT, formulate a theoretical framework, and construct synthetic datasets exhibiting an AOT, while also considering the implications as model sizes tend to infinity. The experiments are conducted on the CC100 dataset using both forward, FW, and backward, BW, models trained with the same specifications to identify differences in model performances solely due to token prediction order. Section: Models, Hyperparameters and Training. In our experiments, we mainly used a type of model known as the decoder-only transformer, which is similar to GPT, and we made some modifications to it. For these experiments, we included features like learned positional embeddings and set the dropout rate to 10%. Depending on the specific experiment, we might adjust other settings, which you can find detailed in the appendix. We consistently used the AtomW optimizer to help with learning, setting the initial learning rate to 0.0001. We also used a specific learning rate schedule that starts with a warm-up phase and then uses cosine annealing with warm restarts to adjust the learning rate. This approach to adjusting the learning rate was mostly the same across our experiments, though we sometimes changed the timing of the warm restarts to match the end of a training cycle, as detailed in the appendix. In our results section, we share findings from various experiments that show the presence of what we call the arrow of time, AOT, in datasets for English and French, and we also provide strong evidence that this phenomenon exists universally across natural languages by looking at 6 additional languages from 5 different language families. Starting with English and French, we analyzed how models trained in the forward, FW, direction compared to those trained backward, BW, using a GPT-2 medium model with about 405 million parameters and a context window of 256 tokens. We trained both FW and BW models on the CC100 datasets for English and French for what amounts to 1 epoch of the French dataset, which is about 27 billion tokens, to avoid the models just memorizing the data. We noticed that after a brief initial period, the loss for the BW model started to diverge from the FW model, settling slightly higher and then moving almost in parallel. This consistent difference, even through the warm restarts, suggests the AOT exists in both English and French. By the end of training, the loss for the English FW model was 2.88 compared to 2.902 for the BW model, a difference of plus 0.76%. For French, the FW model had a loss of 2.788 compared to 2.862 for the BW model, a difference of plus 2.65%. The impact of this phenomenon varies between English and French. We also looked at how the size of the context window affects the AOT, theorizing that with very short context lengths, the AOT would be negligible since models have fewer options for solving the problem. For example, with a context length of just 2 tokens, models are essentially learning the frequency of pairs of words, which should be equally straightforward in either direction. However, we expected the AOT to become more apparent with longer context lengths. To test this, we trained the same GPT medium model with context lengths ranging from 16 to 512 tokens in both English and French. Our findings showed that the AO's magnitude in both languages increased with the context size, highlighting the role of long-range dependencies. We also explored how the size of the GPT models affects the AOT. Intuitively, smaller models might struggle more with capturing long-range dependencies, which are crucial for the AOT. We trained GPT models of various sizes, from 5 million to 405 million parameters, all with a context length of 256 tokens. Our observations confirmed that the AOT is less pronounced in smaller models but becomes more significant as the model size increases. Interestingly, larger BW models generally performed better than smaller FW models. Lastly, we extended our investigation beyond GPT models to include other autoregressive models like GRUS and LSTMs, training models of 3 different sizes with a context length of 256. Our results showed a consistent AOT across different model types for sufficiently large models, suggesting that the AOT is not unique to transformer models but is likely a characteristic of the dataset itself. For the English dataset, smaller BW models even slightly outperformed the FW models, though this advantage disappeared with larger context sizes and models. Section Summary. The section discusses the models, hyperparameters, and training methods used in the experiments, primarily focusing on the decoder-only transformer, GPT, with specific hyperparameters and the AtomW optimizer. The results confirm the presence of an arrow of time, AOT, in English and French datasets, showing consistent differences in training dynamics between forward, FW, and backward, BW, models. Additionally, the influence of context window size and model size on the AOT is explored, with larger context sizes and models exhibiting a more significant AOT effect. The study also extends to other autoregressive models like GRUS and LSTMs, indicating the intrinsic nature of the observed AOT across different models and datasets. Section: Other languages. We found that the phenomenon known as the arrow of time, AOT, exists not only in English and French but also in other languages. We were curious if this was a common feature across all natural languages. To investigate this, we trained 2 different sizes of models, GPT-2 Medium and GPT-2 XL, on 6 additional languages. Our findings showed that an AOT is present in all these languages, though its strength varies, hinting at a possible universal trait among human languages. We also considered whether the way we break down text into manageable pieces for the computer, a process called tokenization, might influence our results. Since the method we used favors a forward direction, we tested if this could be causing the AOT by flipping one language, Greek, backwards and retraining our model. The results were clear. The direction of tokenization didn't affect the AOT, confirming its presence is not due to this factor. From our experiments, we've learned several key points. The AOT is a consistent finding across different languages, model sizes, and settings, especially when the models are large and trained for a sufficient time with a wide context. The strength of the AOT increases with the length of the text context, suggesting that understanding long-distance relationships in text is important. This phenomenon isn't limited to GPT models. We observed similar outcomes with other types of models, indicating that AOTs are a fundamental aspect of the datasets themselves. The impact of the AOT varies by language, which is an intriguing puzzle we're still trying to solve. We also explored why AOT might be easier to observe in some situations than others. We theorized that certain information might be more challenging for backward models to either represent or learn compared to forward models. To illustrate this, we used the example of prime number multiplication, a process that's straightforward in one direction but notoriously difficult to reverse. This difficulty in reversing certain operations could contribute to the AOT. In a more detailed exploration, we created a synthetic dataset based on multiplying prime numbers and then reversing the order of the digits in the product. This setup was designed to test how well models can learn to perform operations in both forward and backward directions. The experiment aimed to mimic the computational challenge of reversing certain operations, akin to the challenges in asymmetric cryptography, where decoding without the key is extremely difficult. In summary, Our research suggests that the AOT is a widespread and intriguing feature of natural languages, influenced by the complexity and length of text contexts. The variability of the AOT across languages and its presence in different model types point to deep, underlying principles in language processing and information theory. Section summary. The experiments demonstrate the presence of an arrow of time, AOT, for English and French, and this phenomenon appears to be universal across various human languages. The magnitude of the AOT varies between languages, but consistently emerges for large models with a long training duration and a large context window. Additionally, the direction and presence of the AOT are universal, but its magnitude is influenced by the language and context length. The section also discusses the computability and irreversibility of the AOT, using mathematical models to illustrate the computational difficulty of reversing certain information-preserving operations, such as number factoring. Section: Gnats of entropy. We're diving into the concept of entropy, specifically looking at how it plays out in our experiments. Entropy, in simple terms, is a measure of uncertainty or randomness. We calculated the total entropy for certain operations involving prime numbers, without focusing on individual elements or specific symbols, which we considered to have zero entropy. For example, when we look at prime numbers less than 100,000, the entropy is about 9.17 nats. Nats are a unit of measurement for entropy, similar to bits but based on natural logarithms. When we arrange these prime numbers in a certain order, the entropy slightly decreases because the order provides some information that reduces uncertainty. Specifically, the entropy for one prime number drops to 8.98 nats, and on average, to 8.67 nats for the second prime number in a pair. Combining these, the total entropy for a pair of prime numbers is about 17.64 nats. This calculation considers the slight reduction in entropy due to the ordering of the numbers. When we reverse the product of these prime numbers, the entropy doesn't change because it's entirely dependent on the original prime numbers. However, when we read this reversed product backward, all the entropy focuses on it, since the rest of the information is already determined. In our experiments, we trained a model on a dataset of prime number products using a GPT-2 medium architecture. The model performed well in forward, FW, mode, closely reaching the theoretical limits of entropy for the prime numbers and their products. However, in backward, BW, mode, the model struggled, especially with identifying the reversed products of the prime numbers. This indicates that while the model can learn to multiply prime numbers, it finds it much harder to factorize them, i.e., to find the original prime numbers from their product. The difference in performance between the FW and BW models highlights a significant asymmetry of training, AOT, in our dataset. This AOT is mainly due to the inherent difficulty in factorizing numbers compared to multiplying them. The forward model nearly perfectly recognizes prime numbers and their products, but the backward model struggles significantly with the reversed products, indicating a much higher difficulty level. This experiment underscores the challenge of learning certain mathematical operations compared to others and suggests that as models and training times improve, multiplication might become easier to learn, while factorization remains a tough nut to crack. This difficulty is not just about the size of the dataset or the model but also about the fundamental computational challenges involved in these operations. Additionally, we noted that the length of the context, or how much information the model can consider at once, plays a crucial role in its performance, especially in forward mode. In summary, our exploration into entropy, prime numbers, and model training reveals significant challenges in machine learning, particularly in understanding and predicting the outcomes of complex mathematical operations like factorization. Section summary. The section discusses the computation of aggregate entropy on prime numbers and their products, as well as the experimental results of training a GPT-2 medium model on the dataset. It highlights the information theoretical limits reached by the FW model for multiplication, while the BW model struggles with recognizing products of prime pairs, indicating a significant asymmetry in the model's abilities. The section also emphasizes the importance of long-range dependencies and the computational difficulty of inverting a bijective function in understanding the asymmetry of the model's performances. Section: Binary Operations. In this section, we explore how a certain type of pattern, which we call an advantage of time, AOT, can emerge in datasets, particularly focusing on why this happens in natural language and why it tends to favor forward, FW, models over backward, BW, models. We create artificial datasets that simulate conditions under which an AOT might arise, using operations on strings of bits, and we investigate how the complexity and structure of these datasets can explain the observed advantage of FW models. We start by looking at synthetic datasets that involve operations on M-bit registers, which can be thought of as strings of M bits where each bit can be either 0 or 1. We're particularly interested in operations that are linear, meaning they can be described by simple rules that apply across the entire bit string. We relate the ease of learning these operations to how many of the bits can be ignored, which we call sparsity, and we use this to explain why FW models might have an advantage over BW models. We also conduct experiments to support our theory and discuss how these ideas might extend beyond linear operations. To get more specific, we consider a scenario where we have sequences of 2 meters plus 1 bits, and we're looking at how 1 meter bit string can be transformed into another through a specific kind of operation, a bijective linear map. We say that an operation is sparse if it involves changing a relatively small number of bits. Intuitively, if the operation that transforms the input to the output, or vice versa, is sparse, it should be easier to learn. This concept helps us understand why FW models might outperform BW models in certain cases. If the operation in the forward direction is sparse, it's easier for FW models to learn, and if the operation in the backward direction is less sparse, it's harder for BW models. We also present a simple communication scenario to illustrate how sparsity in the direction of learning, FW versus BW, can affect the ability to learn new languages. Imagine two people, Alice and Bob, who already know a common language and are trying to learn a new one from each other. If the new language can be described by a sparse operation from the old one, it's easier for them to learn it. We suggest that this scenario naturally leads to a situation where languages evolve to be more easily learnable in the forward direction, creating an AOT in favor of FW models. In summary, we've shown through synthetic datasets and theoretical scenarios that the sparsity of operations on bit strings can explain why FW models might have an advantage in learning over BW models, especially in the context of natural language. This work helps us understand the underlying reasons for the observed performance differences between FW and BW models and opens up new avenues for exploring how languages evolve and are learned. Section Summary. In this section, the authors introduce synthetic datasets based on operations on the space of M-bit registers identified with F2 meters. F2 denotes the field of integers mod 2. They focus on languages based on F2 linear circuits and relate their learnability to their sparsity, providing an explanation for the difference between FW and BW learnability. The emergence of an AOT in a linear language is shown to be related to the sparsities of the forward and backward linear maps, with a communication setup demonstrating the importance of sparsity, particularly FW sparsity, in the presence of a FW AOT in natural languages. Section: Experimental Results. In this section, we share the results of our experiments that back up the points we've made earlier. We started by looking at a group of languages that can be described with straight lines, involving elements from a specific mathematical set, and we varied how thinly spread the connections in these languages were. We trained a model known as GPT-1 on these languages and observed that the ones with fewer connections were easier for the model to learn, as shown by the lower losses in our results. In another experiment, we tested how well a model could adjust to small changes in a language it had already learned, provided the changes kept the language sparse. We trained two types of models on a basic language setup and then introduced minor changes to see how they coped. The results, which we've detailed in a table, showed that the forward predicting model was better at adapting to these changes after a series of adjustments. Moving on to more complex languages that don't follow a straight line and involve more complicated functions, we had to rethink what we mean by sparse. In this context, a sparse setup means using fewer basic operations like AND, OR, and XOR. We found that trying to reverse these complex setups is generally much harder, hinting at a broader principle in computer science that reversing certain processes is computationally difficult. This difficulty suggests there's a natural direction or arrow of time in how these models learn, with forward models possibly having an edge in certain situations. In our discussion, we delve into the capabilities of models that predict one piece at a time and compare two types of models in terms of how well they understand different datasets. Surprisingly, we found that forward predicting models consistently outperform backward predicting ones in terms of perplexity, a measure of prediction difficulty, especially as the models get larger and deal with longer data sequences. This difference seems to stem from the way data is structured over long distances. We propose that this arrow of time in language processing might be explained by the complexity and sparsity of the data. We created synthetic datasets to show how this asymmetry could naturally occur. Our findings open up many questions for future research, such as whether this phenomenon is universal across all languages, how it varies across different types of data, and its relationship with computational complexity. We conclude by suggesting that the arrow of time concept could reveal deep structural features in data and might be broadly applicable across various fields. Understanding its theoretical basis could link it to fundamental principles in complexity theory. We'd like to express our gratitude to several colleagues for their insightful discussions and to various foundations and grants for their support.